Hello students, in the last video we have seen the heat generation cases in the slab, cylinder and as well as the sphere. Now having seen the heat generation cases in all kinds of geometries, now let me apply those particular principles of heat transfer pertaining to the heat generation cases to this important problem given in GATE 2022. This is a problem given in GATE 2022 is definitely a very good problem because this problem has non-uniform heat generation. In all the earlier cases whatever I have done until now, earlier cases of heat generation until now whatever I have done, they are dealing with uniform heat generation. That means Q dot is a constant everywhere throughout the body, maybe a slab, maybe a cylinder, maybe a sphere. Throughout the body there is a uniform heat generation. At every location same amount of heat is being generated. So that was the assumption we have made out in the earlier cases. But this problem deals with the non-uniform heat generation. See, let us look into this problem given in the GATE 2022. Very good question. Look at the question there. Consider a rod of uniform thermal conductivity. Conductivity is constant, whose one end x is equal to 0 is insulated. So there is a uniform rod of a length L. There is a insulation. This end of the rod is insulated, okay, and other end is exposed to the flow of air. There is a flow of air here, air flowing. Other end, the temperature of the air was given. This is the L is the length of the rod. Okay, A is the maybe area of the rod, cross-sectional area of the rod, and with a convective heat transfer coefficient H. This is a convective heat transfer coefficient associated with the fluid is H. The cylindrical surface of the rod is insulated. That means all the surface has been insulated. That means you are fixing the heat conduction exclusively along the x direction. This as the x direction. You are assuming that conduction heat transfer is happening only along the x direction because this surface is insulated. There cannot be any conduction happening along the radial direction. Okay. The rate of internal heat generation per unit volume inside the rod. This is the very important thing. Q dot, Q dot is a function of x. This Q dot is that is heat generated per unit volume. It is a function of x. Look at this particular function. Q dot is cos 2 pi x by L, where Q dot is the heat generated per unit volume. Steady state conditions are prevailing. The temperature at the midsection of the rod, exactly at the midsection of the rod, temperature is recorded as TA under steady state conditions. What will be the temperature at the same location if the convective heat transfer coefficient H gets doubled, becomes 2H. So initially the convective heat transfer coefficient is H, the end of the rod is exposed to the air temperature is T infinity if you think that, and there is a non-uniform heat generation because look at that Q dot, heat generated per unit volume is a function of x, cos 2 pi x by L, where L is the length of the rod. The temperature at the exactly at the midpoint of the rod is TA. In case if that H becomes 2H, what will be the temperature at the midsection of the rod? In fact, this is a very good problem. So now let us go to the first principles. What are the first principles? The conservation of energy for steady state. So based on that first principles, conservation of energy by taking a small differential element, first of all let me derive an equation for the temperature distribution of the rod along the x. So my objective now is to calculate what is the temperature distribution of the rod along the x direction given the boundary conditions. What are the boundary conditions? He has indirectly mentioned one end of the rod is insulated. Okay, this end of the rod is insulated. The other end of the rod is losing heat only by convection, to the air. Okay, at x is equal to L, there is a convection heat transfer occurring between the end of the rod and the air. There is no radial conduction. We strictly look at this. Heat transfer is strictly along the axis of the rod. This is the direction of the conduction, that is along the x direction. So this is a situation for which I consider a energy balance. I will consider a small differential element I will consider a small differential element of length dx, What is the heat entering? What is the heat entering and what is the heat conducted out? Okay, I write the energy balance and what is the heat generated inside that differential control volume of length dx. From that I will formulate the differential equation. I will integrate that to get the temperature distribution. Okay, first consider a differential length for a differential element, of length dx. For a differential element of length dx for steady state, conditions are steady. That is very important. What do you mean by steady state? The temperature at a particular location must not change with respect to the time. For steady state, what is the energy balance? Qx, heat conducted into the element along the x direction, plus Q generated inside the element should be equal to the heat conducted out, Qx plus dx. Okay, what is the Q generated? Q generated will be Q dot into ADX. ADX is the volume of the element. Always Q dot is the heat generated per unit volume. Okay, ADX is the volume of the element. If A is the cross-sectional area of the rod, what is the A into dx? That is the volume of the element. Okay, consider it there. Okay, then so I write what is that Qx? Qx is plus what is the Q generated? Q dot into ADX. What is that Qx plus dx? Qx plus dx will be Qx plus dou by dou x of Qx into dx. Qx plus dou by dou x of Qx into dx. These two will get cancelled. Q dot into ADX is equal to, what is that Qx there from the Fourier law of conduction? Minus Ka dt by dx according to the Fourier law of conduction. How did I write this Qx plus dx as like this? Because this is the rate of change. If you just take the differential element, if Qx is the heat conducted into the element, that rate of change of Qx for a differentially small increment in x is given by this dou Qx by dou x. Then if dou Qx by dou x is the rate of change of Qx for a differentially small increment in x, what is the change for a distance of dx? That is dou Qx by dou x into dx. So this is indicating the change in Qx for a distance of dx. Add that change to the Qx to get the Qx plus dx. Try to understand how I have written that Qx plus dx. I have just taken the dou Qx by dou x, that is the rate of change of Qx for a differentially small increment in x. The rate of change is multiplied by dx to get the total change in Qx for a distance of dx. Add that change to the Qx to get the Qx plus dx. Okay. Now, and this ADX also gets cancelled. Then it will become by rearranging the parameters k into d square t by rearranging the parameters d square t by dx square. This no d by d square is equal to minus q dot by k. Integrating with respect to x, dt by dx both sides is equal to minus 1 by k integral q dot dx plus c1. Now already we have got the q dot as a function of x, cos 2 pi x by L. I substitute that dt by dx is equal to integral cos 2 pi x by L dx plus c1. dt by dx is equal to minus 1 by k. What is cos 2 pi x? Integral cos 2 pi x by L sin 2 pi x by L. Okay, divided by divided by 2 pi by L. That will go to the L will go to the numerator into L by 2 pi plus C1. Okay. And we have got one important boundary condition. If you just look at this figure, at x is equal to 0, x has got two limits, x is equal to 0 and here x is equal to L. Okay, at x is equal to 0, the rod is insulated. That means there cannot be any conduction, heat transfer can happen. Because rod is insulated, no conduction could happen. Okay. At x is equal to 0, rod insulated, Q conduction is 0. When Q conduction is 0, Q conducted is equal to 0 minus Ka dt by dx is equal to 0, implies dt by dx is equal to 0 at x is equal to 0. That means if we just substitute that at x is equal to 0, dt by dx is 0. What is at x is equal to 0? Sin 0 is 0. So all this will vanish and this will become dt by dx is 0. That is, from this boundary condition we can say C1, the one constant of integration, has vanished. C1 is 0. Okay. C1 has become 0. Now that C1 has gone. Now considering again integrating this particular one, that is, you are integrating this equation. After confirming that C1 is equal to 0, so this L I bring it right side, L by it becomes minus L by 2 pi k, integrating with respect to x again, T is equal to, look at this, T is equal to minus L by 2 pi k minus L by 2 pi k integral sine 2 pi x by L dx plus constant of integration C2. Because it is a second order equation, we should get two constant of integration. That implies it becomes T is equal to, so that becomes minus L by 2 pi k. What is integral sine 2 pi x by L? Minus cos 2 pi x by L into L by 2 pi plus C2. So this minus it becomes plus. So it becomes L square by 4 pi square k into cos 2 pi x by L plus C2. This is the temperature now. But this, how to get the C2? C2 will be obtained from the second boundary condition. What is the second boundary condition? Look at this. For steady state, the heat conducted at x is equal to L should be equal to the heat convected. So whatever the heat conducted here, because at the edge there cannot be any storage of heat. At the edge of the rod there cannot be any storage of heat because that edge of the rod carries zero mass. So whatever the Q conducted into the edge should be equal to the Q convected from the end of the rod to the fluid. Okay. At x is equal to the second boundary condition, the second boundary condition is at x is equal to L, that is edge of the rod, that is end of the rod, that is edge of rod, heat conducted into the end edge, heat conducted in should be equal to the heat convected out. Heat convected out from end to fluid to air. What is the heat conducted in? minus Ka dt by dx at x is equal to L at end of the rod. See this is the boundary condition. Once again, the second boundary condition I am explaining. This heat conducted at the end of the rod here, no, heat conducted should be equal to the heat convected, because that end of the rod cannot store any heat. It has no mass. The end of it has area but no mass. So therefore it cannot store any heat. Heat conducted into that end should be equal to the heat convected out. Convected to what? Convected to the air. But how do you get the convection law? Convection is always given by Newton's law of cooling. HA temperature at x is equal to L minus T infinity. A gets cancelled, right? So now we got the dt by dx. Is equal to dt by dx is equal to minus h by k into temperature at x is equal to L minus T infinity. But already we got the dt by dx. Look at this. This is the dt by dx. C1 is equal to 0. C1 has become 0. So at x is equal to L, what is that? If we just write at x is equal to L, what is the, that means at x is equal to L means cos 2 pi. Cos 2 pi means cos 2 pi is cos 2 pi, this will become, right. So this particular now if you have the dt by dx, I just substitute at x is equal to L, and then I write the dt by dx at x is equal to L here, this situation, right. What is the dt by dx at x is equal to L? I'll just check it up. Dt by dx here, dt by dx here, dt by dx at x is equal to L. Now if you write minus k into, what is the dt by dx? Sine 2, right, minus 1 by k, minus k into minus 1 by k sine 2 pi L by L, no, that x is equal to L should be equal to the h into temperature at x is equal to L minus T infinity. So what is sine 2 pi? Sine 2 pi is 0. All this will become 0. Then it will become, from this we can say temperature at x is equal to L is T infinity. If you substitute that one here, look at this, temperature at x is equal to L is T infinity. That means you have to keep the L here. So all this will become 1 there. Cos 0 is 1. So this becomes, so that what is, we can get the temperature at x is equal to L has become T infinity. Therefore, substituting in a T function, substituting in function of T. Now look at this. Here temperature at x, you have to keep at x is equal to L. Here you have to keep temperature at x is equal to L. Temperature at x is equal to L, which is equal to T infinity, is equal to, substitute here, substituting this function, minus it becomes, this minus it becomes L, it becomes here, in this I am substituting, L square by 4 pi square k, L square by 4 pi square k, right. Cos, if we put x is equal to L here, we have got the temperature as a function of x, right. It becomes cos 0 is 1 plus C2. Therefore, C2 will become T infinity minus L square by 4 pi square k. So we got the temperature as a function of x. Finally, what is the temperature as a function of x? L square by 4 pi square k, L square by 4 pi square k, here cos 2 pi x by L, cos 2 pi x by L plus C2, okay, plus C2. What is that C2? T infinity minus L square by 4 pi square k. But it does not contain anything. So T is only a function of x. But not a function of h, not a function of h. So this is the one I conclude. T is only a function of x, but therefore even if h gets doubled, temperature, what is the temperature there? We have noted as Ta, temperature Ta at this, at this location. Ta remains same temperature at this location, at the mid location. T is only a function of x, but not a function of h. Ta remains same. That is the answer. Answer will be, just look at the answer. What is the answer given? Ta will remains same. Answer will be C. C is the answer. C is the answer. Very good question. We have used the two boundary conditions, heat conducted is equal to 0. Here heat conducted is equal to heat convected. Now from that we got the temperature at x is equal to L. That is substituted in the temperature function to get the C2. So there are two boundary conditions. One boundary condition is insulated boundary condition where the heat conducted is 0. At x is equal to L, heat conducted is equal to heat convected. So this kind of a boundary condition utilization, how to write the boundary conditions after writing the generalized equation for T, that is very, very important in the heat transfer problems. Heat transfer is all about writing a differential equation and integrating that and getting the constants of integration to get those constants of integration from the given boundary conditions like this. Okay. So this is an excellent question. Look at this. This is also heat generation. Consider a steady state one-dimensional heat conduction in an infinite slab of thickness 2L. The thickness is 2L here. This thickness is 2L. Okay. L is equal to 1 meter. This is 1 meter. This is 1 meter. Okay. The conductivity K of the material varies with the temperature as K is equal to Ct, where T is the temperature in K and C is a constant equal to 2. K is equal to 2T. It is a variable thermal conductivity. There is a uniform heat generation of Q dot. If both the faces of the slab are maintained at 600 K, what is the temperature at the midplane? It is the uniform heat generation case, but variable conductivity. Such kind of a problem we have done earlier also, but there the conductivity of the material is constant. It is not a function of x, it is not a function of temperature, but now it is that K is a function of temperature. So it is a variable thermal conductivity. Look at this problem there. So I will begin with the generalized one-dimensional conduction equation from which is obtained from the generalized conduction equation with uniform heat generation, because steady state conduction one-dimensional with uniform heat generation. So this is the equation, right? So implies d square T by dx square is equal to minus Q dot by K or otherwise K into integrating dt by dx So before writing this, I would like to write like this. This same equation I could write it as d by dx of, because k is a variable, is equal to minus q dot, because k is a variable, right? Now integrating k into dt by dx is equal to minus q dot x plus c1. Instead of k, I write that 2t. as that 2t dt by dx is equal to minus q dot x plus c1. 2t dt is equal to minus q dot x plus c1 dx. Integrating 2 into t square by 2 minus q dot x square by 2 plus c1x plus c2. This 2 will get cancelled. So, this is the, we got the C1 and C2 to be obtained, we got the two boundary conditions. We got the two boundary conditions at x is equal to plus L and x is equal to minus L. Based upon this particular given boundary condition, temperature is same, T is equal to 600 Kelvin. That means to satisfy this, that is C1 must be 0. Then only both sides you will see the same temperature. This kind of logic I had given in the earlier case also. Okay. Here the K is the variable thermal conductivity. So, at x is equal to plus L and minus L, C1 is becomes 0, and the second boundary condition will be, he has given the 10 power 6, right. C1 has become 0, and at x is equal to 0, look at that question, that is a second boundary condition. At x is equal to plus 1, at x is equal to plus 1, if you write, so t square, what is that, 600 square, 600 square is equal to minus q dot is how much, q dot is a kilowatt, 1280 into 10 cube into 1 square by 2 plus C2. C1 has already, because otherwise C1 into 1 plus C2. At x is equal to minus 1 implies 600 square is equal to minus 1280 into 10 cube into minus 1 whole square by 2. I am substituting the minus C1 into 1 plus C2. Okay, we got two equations and two constants. We can easily obtain that C1 has become 0, you will get the C2 as 1000 Kelvin. C1 will be 0 and C2 as 1000 Kelvin. Then put x is equal to 0. Obviously, when you put x is equal to 0 here, you will get the C2. Therefore, temperature at x is equal to 0 is equal to C2. Answer is 1000 K. By adding and subtracting these two equations, you will get the C1, C2 values. This is also a question given in the GATE 2022. Please note that here it is a variable conductivity. Since variable conductivity, this is written like this. Going to the fundamentals of the equation which are derived in the earlier case, earlier I have derived, right. You look at the basic derivation of the generalized heat conduction equation. That time, because in that derivation K was assumed as constant, it was taken out to obtain this. Okay, so when K was taken out, you will get this. If the K was not taken out, because K is a function of temperature or a function of X, K is a function of X, then this is the result. Okay, we look at the, just recall the derivation I have done in the first case of the generalized heat conduction with uniform heat generation. Okay, just recall the derivation I have done in the earlier case while deriving the generalized conduction equation with constant q dot. There I have assumed that K was a constant that was taken out, assuming steady state. In case if the K was a variable, K will be inside the bracket. After integration, you get the T as a function of X with the two constants of integration C1, C2. Those two constants of integration are obtained from two boundary conditions. This is 1 meter, this is 1 meter as given. L is the total is 2L, this is 1 meter, this is 1 meter. At x is equal to plus 1, 600 Kelvin. At x is equal to minus 1, it is again 600 Kelvin. I have substituted that and we got the C1 is 0 and C2 as 1000 Kelvin. Okay. So, once we put in this temperature distribution at x is equal to C1 has already become 0. At x is equal to 0, whatever the temperature will be, that will be at x is equal to 0. What is the temperature you get? That will be the C2. Look at this. And if you just put x is equal to 0, this will vanish. This is already vanished. Whatever the temperature you get, that will become the C2. Therefore, temperature at x is equal to 0 will be the 1000 Kelvin. So, the very important cases of the heat generation problems I have done. Look at this question. Consider one-dimensional steady-state heat conduction through a plane wall with a boundary surfaces at x is equal to 0 and x is equal to L. There is a uniform heat generation. Here x is equal to 0, here x is equal to L. There is a uniform heat generation clearly as mentioned. Q dot is a constant. Please note that you consider the heat generation only when it is mentioned in the problem. Most of the occasions it will be uniform. In the earlier problem I have done cos 2 pi x by L. So, that was the situation where the uniform heat generation will not be prevailing. It is a non-uniform heat generation because Q dot has become a function of x, but that is the rarest situation which was given in the GATE 2022 problem. But for that, most of the occasions, majority of the GATE problems, you will assume that there will be a uniform heat generation. Q dot is a constant. Sometimes there may be non-uniform, but still the energy balance still prevails. I have done in the earlier one more problem also. There are 3 slabs, only the central slab is generating heat non-uniformly. So, there also we have written the energy balance for steady state conditions. As long as the conditions are steady, even when there is a heat generation, whether it is uniform or a non-uniform, total heat generated in the entire control volume must be equal to the heat convected. That principle never forget. That is the energy balance. So, this is a uniform heat generation and heat is generated uniformly and left hand side temperature is maintained at 0 degrees Celsius. Right hand side maintained at 100 degrees Celsius. That means both sides the temperatures are different. I already said when the temperatures are different and nothing is insulated, you will get the unsymmetric parabola. This is an unsymmetric parabolic temperature distribution. Unsymmetric parabola. Right? When there is unsymmetric parabola, the maximum temperature will be definitely in the right half. This is the maximum temperature which is in the right half. Okay, the direction of the heat transfer, he has given that the direction of heat transfer from the 100 to the surface at 0. Wrong. That is because how can the heat flow from uphill? The direction of the heat transfer at 100 degrees Celsius, it will be rightwards only. If this is the direction of heat flow preceded by conduction here. Convection at the boundary is always preceded by the conduction at the boundary. So, this is the direction of the heat flow here is rightwards. Heat cannot flow from low temperature to the high temperature. See here this is the temperature profile here. More maximum temperature here, lesser temperature, lesser, and this is the 100 degrees Celsius. The maximum temperature must be greater than 100 degrees Celsius, correct? The temperature distribution is linear. It is not linear, it is a parabola. The temperature distribution is symmetric. It is not symmetric, it is unsymmetric. Why it is unsymmetric? Because both sides temperatures are different. It is an unsymmetric. So, answer will be B. The maximum temperature will be definitely more than 100 degrees Celsius. Nothing is insulated. Here also there is a convection. Here also there is a convection. So, but that convection is preceded by the conduction here. There is a Q conduction happening. Convection happening at the boundary is always preceded by the same amount of the conduction at the boundary. Look at this, convection at the boundary is preceded by the same amount of the conduction at the boundary. That is true at the left hand side surface and also the right hand side surface. Here also, look at this, convection at this surface is preceded by the same amount of conduction at that surface. Both these two must be equal. Again, these two must be equal. I can also say that the total heat generated in the entire slab should be equal to the heat convected from right side plus heat convected from the left side. That energy balance always holds good, whether it is a uniform heat generation or a non-uniform heat generation. Now I will start a new topic in conduction chapter called fins or extended surfaces. This is also an important topic in the gate point of view. What are fins, why they are provided and where they are provided practically. First, let us understand about what are fins, why they are provided and where they are provided. Fins are the protrusions from a solid surface. They are projections from a solid surface into the atmospheric air, and they are provided to increase the heat transfer rate from that solid surface to the air. Okay, fins are the protrusions. Fins are the projections from a hot solid surface into the atmospheric air, and they are provided to increase or to enhance the heat transfer rate by providing more heat transfer area. How do the fins increase the heat transfer rate? They are providing more surface area of heat transfer, or they are providing more convection area of heat transfer. That is how the fins can increase the heat transfer rate. Then question comes, where they are provided? They are provided in so many practical applications: IC engines, refrigerator condenser tubes, air conditioner condenser tubes, automobile radiators, electronic devices, electric motors. There are so many practical day-to-day applications which we may observe that fins are always there. Fins are protrude from a solid surface. Okay, fins, they are the projections. They are the projections protruding from a hot surface into atmospheric air, and they are meant for increasing heat transfer rate, by providing more heat transfer area, or convection area. Because we know that any mode of heat transfer is directly proportional to the area of heat transfer. In convection, what is the convection area? The area of exposure or the area of contact between the solid surface and the fluid is the convection area. So that convection area is increased because of providing the fins. That is how we increase the heat transfer rate. Examples, so many things I can give. IC engines. Best example is IC engines. All the air-cooled IC engines, more correctly, air-cooled IC engines, two-wheelers. All two-wheelers cylinders will have the fins. You can see in your bike there are fins around the cylinder. You can easily see that. And now good number of fins you see. Reciprocating air compressors. Positive, they are also called positive displacement type of compressors. Reciprocating air compressors or positive displacement type of compressors. Any compressor that requires cooling. When you provide the cooling to the compressor, the work of compression will be lesser. That is why we provide the cooling to the compressor. Particularly in the reciprocating air compressors, we provide the cooling by providing the fins around the cylinder. You can easily observe positive displacement, belt driven, slow running, positive displacement compressors generally observe in the air filling stations, slow running there. They are not the centrifugal machines, rather they are the reciprocating machines where around the cylinder you see the fins. And electric motors and transformers. Electric motors require cooling and electric transformers require cooling. Transformers also require cooling. Electronic devices in your CPU, in your central processing unit of the desktop computer system, electronic devices. IC engines, and so many. You can give many, and automobile, a radiator, car radiator. You have the fins, automobile radiator or car radiator. Above all, refrigerator and AC condensers. Refrigerator and AC condensers. Air conditioning unit, AC, your condenser units. You see the fins. And you observe that in all these examples I had given, the coolant, in all these examples which I had given, the coolant around the fin is air. Coolant around the fin, in all the examples, around the fin is atmospheric air. That means you will never give me an example where the coolant around the fin is water. Fins are never used with water. Whenever we are observing the fins, by default, I can say the coolant around the fin will be atmospheric air, the surrounding like air present in the atmosphere. You can't give me an example where the fluid around the fin is water. We don't use fins. We don't have to use fins when water is the coolant. Why like that? You will come to see later. Fins are always used only when the H is low. That is, I am giving the important point here, that is, fins are always used only when H is low, that is with gases. Only with gases H value is low. When H is high, that is with water, we don't need fins. We don't have to keep the fins. It is a mere waste of money keeping the fins. Okay, now we have seen what are the fins, where they are used, why they are used, etc. Now let us go to the analysis of the rectangular fin. Analysis of rectangular fin. First, I am just giving the how a fin looks like, the configuration of the fin. I am drawing the figure. This is the rectangular fin of length L. L is the length of the fin. Z is the width of the fin. And T is the thickness of the fin, and A is the profile area. This location of the fin is called root of the fin. This is called base wall. This is the x direction. Here x is, this is the end of the fin or tip of the fin. X is equal to L. This is called as the tip of fin. L is the length of fin. This is the base wall at T0, root temperature. This is the fin, rectangular fin attached to this base wall, which is at a temperature of T0. The location where the fin is attached to the base wall, the location where the fin is attached to the base wall is called as the root of the fin, where the x is considered as 0. And z is the width of the fin. And t is the thickness of fin. T is the thickness of fin. Out of the 3 dimensions, thickness is very small. We have the length, width, z and thickness. Among all the 3 dimensions of the fin, thickness is very small. It may be meagerly just 2 mm or 1 mm or 3 mm, like that. The thickness of the fin will be. A is called profile area of the fin. A is the profile area of fin, which is given by z into t. A is called. So sometimes the fin could be of this kind of a configuration. This kind of a fin is called as a pin fin, like this. That kind of a fin is called as the pin fin, where the circular in cross section. Okay, this also can be but mostly we will analyze the rectangular fin. A is called profile area, L is the length, and the surrounding fluid will be atmospheric air. By all means, it is atmospheric air at T infinity. So there is a convection happening from the surface of the fin to the air, convection with H watt per meter square Kelvin. So this is the situation. This is the situation what we are observing in the fins. So in this analysis of the fin, this kind of a fin is called as a pin fin, circular in cross section. Okay, we will analyze it. In fact, rectangular fin and pin fin, same analysis, but only thing is cross sectional area will be different. In the rectangular fin, the area of cross section, this is the profile area, will be the cross section. If it is a pin fin like this, the area of cross section will be circular. That is. So this is the x direction. X has 2 limits. X is equal to 0 at the root of the fin. This point is called as the root. This is called as the tip of the fin or end of the fin also, they say end of the fin or tip of the fin. So my objective of, first let us understand what is the mechanism of heat transfer. First let us understand what is the mechanism of heat transfer. Then we will try to understand what we are going to find in the analysis. This is the mechanism of heat transfer. First, heat gets conducted into the fin. The only mode of heat transfer happening from the base wall into the fin at its root. The only mode of heat transfer happening from the base wall into the fin at its root is the conduction. Heat enters from the base wall into the fin by conduction mode, and then what happens is the heat keeps conducting along the length of the fin, that is in the x direction. This is a positive direction of the x. Heat keeps conducting, first enters by conduction, and after that heat keeps conducting along the length of the fin, that is in this x direction. Simultaneously, at the same time, heat is also keep convecting from the surface of the fin. All around the fin there is air. Heat keeps convecting from the surface of the fin to the air at a T infinity with a convection coefficient of H. First by conduction, and after that this conduction and this convection both happen at the same instant of time, simultaneously it happens. So that is the actual mechanism of heat transfer. I write that the actual mechanism of heat transfer, you have to understand this mechanism correctly for the fin. The actual mechanism of heat transfer in any fin is, first heat gets conducted into the fin at its root. Root or base both mean the same, that is the root of the fin or base of the fin both mean the same, at its root, and then while conducting along the length of the fin, that is in the x direction, and then while conducting along the length of the fin, that is in the x direction, heat is also simultaneously convecting from the surface of the fin. Heat is also simultaneously convecting from the surface of the fin into the ambient air at T infinity with a convective heat transfer coefficient of H watt per meter square Kelvin. This sentence you have to thoroughly understand. Look at this once again, I am explaining. The actual mechanism of heat transfer in any fin is, first heat gets conducted into the fin. Look at this, into the fin at its root. First heat gets conducted into the fin at its root here. And then while conducting along the length of the fin, that is in the x direction, heat is also simultaneously convecting from the surface of the fin into the ambient air at T infinity with a convective coefficient of H. So this is what you have to understand thoroughly, the mechanism. Okay, this is a length, this lateral dimension is called Z, and this is the thickness. T is too small. More correctly, the thickness of the fin is too small, not small, it is very, very small, maybe few mm, very small or too small. Now, I would like to analyze the fin by considering the small differential element. I consider the small differential element of the fin, of length dx, here, of length dx at a distance of x from the root of the fin. I have considered a small differential element of the fin of length dx at a distance of x from the root of the fin. This is my element. Okay, this is the element. For this element, I would like to write the energy balance by considering the conductions. Qx is the heat conducted into the element. Qx plus dx is the heat conducted out of the element. If this is the conducted into the element, this is the conducted out of the element. But in between there is one more thing, that is the convection. Q convection from the surface of the element of the fin to the air. Qx is the heat conducted into the element. Qx plus dx is the Q conducted out of the element. In between there is a one more heat that is escaping from the surface of the element of the fin to the air, that is Q convection. You can see here conduction into the element, conduction out of the element. In between there is a convection heat loss occurring from the surface of the element of the fin to the air at a T infinity with a convection coefficient of H. Okay. Consider a differential element of the fin of length dx at a distance of x from the root of fin, where the temperature of the fin is T, where the temperature of fin is T. Definitely T is a function of x. T is a function of x. That is my main objective. Actually, my objective of the analysis, first I write here. My objective of the analysis is, the main objective of the analysis is, two objectives are there. First objective is to get temperature distribution, T as a function of x. Temperature is varying from the root to the tip, temperature is decreasing from the, what is the temperature. Second objective is to get heat transfer rate through fin. How much heat is lost through the fin per second? Heat transfer rate through fin. Only one assumption. These two are the objective. In any fin, my main objective will be these two. What are the first one? What is the first one? How do the temperature change from the root to the tip of the fin? What are the two limits of two boundary conditions of x? Two limits of x. One is 0, x is equal to 0 at the root, x is equal to L at the tip of the fin. From the root to the tip, how do the temperature change with respect to the x direction? That is x direction. Is number one. Second objective is, and from the entire fin to the air, how much heat is being lost? From the entire surface of the fin to the air, how much heat is lost? The rate of heat transfer between the entire fin and the air. These two are the main objectives. These two are the main objectives of the fin. Okay. And only one assumption. Assume steady state. Assume only one assumption. Assume steady state. What do you mean by steady state? Temperature is not a function of time. Temperature at any particular location do not change with respect to the time. That is a only one assumption. Now let Qx is equal to heat conducted into the element along the x direction given by the Fourier law minus Ka into dt by dx. Then heat conducted out of the element will be Qx plus dou Qx by dou x into dx. That is, if Qx is the heat conducted into the element, its rate of change with respect to the x for a differentially small increment in x is given by this. When it is multiplied by the dx, what is the change in Qx? What is the change in Qx? Change in Qx for a distance of dx is given by this, because dou Qx by dou x is the rate of change of Qx with respect to the x. For a distance of dx, what is the change in Qx is given by dou Qx by dou x into dx. Add that change to the Qx, to get the Qx plus dx. Okay. And then heat convected from the surface of element to the fluid. Heat convected from the surface of element considered. From the surface of element to fluid is equal to convection means what? We should always write the Newton's law of cooling. Whenever we talk about the convection, Newton's law of cooling will come, HA delta T. But here what is the area of convection? Just look at this figure. What is the area of convection? The convection is happening from this locality, from this top surface of the element, from the sides, from the below of the area of the element exposed to the fluid. And so from all around that element, wherever the fluid is in contact to that, convection is happening. You can see here, convection is happening from this area, from the front area, from the below there is some area will be there which is equal to this. There also air is there. Opposite to that side, opposite to this side, there is another area will be there same as this. So how to calculate that convection area? That can be seen here. Perimeter. If P is the perimeter of the fin, perimeter is given by 2z plus 2t. This is the perimeter of the fin. So perimeter into this dx distance, that is the contact area, convection area between the fluid and the surface of the element, Hp dx into T minus T infinity, where P is the perimeter of the fin, where P is equal to perimeter of fin. That could be more understood clearly if we just consider the pin fin. Supposing if this is the pin fin. Pin fin means what? Fin having the circular cross section. If we just consider the a small differential length of the element, if this is the convection happening, what is the convection happening? From the surface of the element, h into pi d, where d is the diameter of the fin, into dx. Or otherwise I'll write the capital, capital diameter d. So that to avoid the confusion, I will write, if d is the diameter, pi d into dx into t minus t infinity. This is the convection happening from the surface of the element. Okay. If d is the diameter, pi d is the perimeter into dx, that is the convection area of that surface of the element from where the heat is being lost by convection. So convection area is always the contact area. What is that contact area? Pi d into dx, HA delta T. This is the Newton's law of cooling. Same thing I have written there. Here the P is the perimeter. P is the pi d, perimeter of the element there I have considered. Okay. Perimeter of that, see that. Okay. Supposing in the earlier case, if you just look at this, here the perimeter will be this dimension, 2z, z plus z, 2z plus t, 2t. P is equal to 2z plus 2t. That is a perimeter of the fin for the rectangular fin. If it is a circular fin or a pin fin, it is a perimeter will be pi d, where d is the diameter of the fin. Okay. Now, Qx is the heat conducted into this. Qx plus dx is the Q conducted out of this, and Q convected is the from the surface of the element. This is Qx. This is Qx plus dx. Okay, Qx plus dx. And the element is in steady state. That means this entering energy should be equal to the leaving energy. This is entering, this is leaving, this is also leaving. Therefore, for steady state of the element, what is the energy balance says? For the steady state of this element, Qx should be equal to the Qx plus dx plus Q convected from the surface of the element. For steady state of element, because we have already assumed the steady state conditions. Steady state means what? Temperature should not change with respect to time. For steady state conditions of element, Qx, that is the heat conducted into the element should be equal to the qx plus dx plus q convected from the surface of the element. Q convected from the surface of the element here. This is a Q convection, right? So, I substitute that values. What is the Qx plus dx? Qx plus dou by dou x of Qx into dx plus Hp dx into T minus T infinity. Always remember that A is the profile area or the cross sectional area. In any pin formula, pin formula, A refers to the cross sectional area or the profile area. Okay, these two things gets cancelled. 0 is equal to dou by dou x of, what is that, Qx minus Ka dt by dx from the Fourier law into dx plus Hp dx, P is the perimeter, into T minus T infinity. This dx also can be cancelled off. It can be, because that is left hand side is 0. Now K is a constant, which is the thermal conductivity of the material of the fin. K is the thermal conductivity of the material of the fin. A is the profile area. So look at this. A is the profile area perpendicular to the direction of conduction. That is the profile area. That is also a constant. Profile area is also, look at this. Here the profile area marked here. Profile area is a, which is also a constant. So Ka, I can take it outside the bracket and I can divide throughout with Ka. The resulting differential equation will be d square T by dx square minus Hp by Ka into T minus T infinity is equal to 0. Okay. Now I want to, my objective of the analysis, I already mentioned, there are two objectives in the analysis. First objective is to get the temperature distribution along the length of the fin. So to get the temperature distribution, we have to integrate this second order differential equation. But for integrating the second order differential equation, now I am changing the variable from t to into the theta, because in mathematics also we have learnt about some standard format of the second order differential equations. In mathematics also we have got certain standard formats of second order differential equations, for which the solution can be directly just written by seeing the format of the differential equation, we can give the solution. Into such format I want to change this differential equation. So I want to change the variable from t to the theta, so that the differential equation in theta will be of a very standard format, so that we can directly give the solution without any intermediate mathematical jargon. So that I want to change this second order differential equation into that format, for which I am writing let t minus t infinity is theta. When t is a function of x, theta also will be a function of x. Differentiate both sides with x, it will become d theta by dx. If you differentiate one more time, it will be d square theta by dx square, and put m square is equal to Hp by Ka. M square is Hp by Ka. Okay. Now if you substitute these two things here, you will get d square theta by dx square minus m square theta is equal to 0. This is the standard format of second order differential equation. We have seen this format in the mathematics also. This is the standard format of the second order differential equation. The solution of this could be directly. The solution of this will be, solution is theta is equal to C1 into e to the power of minus mx plus C2 into e to the power of mx. C1 and C2 are constants of integration that are to be obtained from boundary conditions. M is equal to, where M is equal to root of HP by Ka. Its units are per meter. C1 and C2 are constants of integration. To be obtained from boundary conditions. Two boundary conditions, because there are two constants, is the second order differential equation. That means the solution will have two constants of integration. We require two boundary conditions to get those two constants of integration to be obtained from boundary conditions. One boundary condition is one common boundary condition, more correctly I can write one common for all the cases of the fin. This is the common boundary condition. One common boundary condition is at x is equal to 0. See, look at this, at x is equal to 0. See this, at x is equal to 0, what is the temperature of the fin? T0, that is the base temperature or the root temperature. If this is the wall, to which the fin is attached, here at x is equal to 0, what is the temperature of the fin? Same as the base temperature, base wall temperature, which is denoted as T0. Okay, here look at this, T0 there. At x is equal to 0 implies T is equal to T0 and theta will be, and that case theta will be theta naught given by T0 minus T infinity. T infinity is the ambient fluid temperature. Okay, standard notations we have to remember. So, the second boundary condition, we require two boundary conditions. Second boundary condition means the boundary condition at this location, here at x is equal to L. The second boundary condition depends upon three different cases. Generally, for each case, the second boundary condition will be different. Generally, in the fins, we come across three usual cases. One is, first case will be fin is very, very, very long, infinitely long fin, very long fin. That is first case. The second case is fin is finite in length, not long, fin is finite in length, but this tip will be insulated. This tip, edge, the edge, this end portion, this edge of the tip is insulated, perfectly insulated. That is the second boundary condition, second case of the fin analysis. Third case is fin is finite in length, but the tip also there is a losing heat by convection. So, there are three cases generally we consider in the fin analysis of the problem, fin problems. One case is very long fin, they will mention in the problem, fin problem, whether it is a very long fin, infinitely long fin or insulated tip case, they will clearly mention in the problem. So, first case will be very long fin, second case will be finite in length but tip is insulated, third is finite in length but tip is not insulated, that means there is a convection heat loss also. The second boundary condition depends upon three different cases of fin. First case, for all the three cases, This is a common boundary condition. At x is equal to 0, theta is equal to theta naught. For all the three cases, this is fixed. But for the each case, the second boundary condition will be different. But for all the three cases, that is the common boundary condition, first boundary condition. Now, I will consider the infinitely, case 1, first case, infinitely long fin case. Case 1. Infinitely long fin case. That is infinitely long, you can also call it as the very long fin. They will mention whenever you have to use this case only when it is mentioned in the problem that it is given a long fin. When the fin is very long, say for example, fin is too long, very long, then what is the temperature at the tip of the fin here? It is same as the temperature as that of the T infinity. Why? When the fin is very long, at this location, this high temperature cannot be sensed there. Because this high temperature of the fin at the base, how can it be sensed at that? Therefore, then the temperature at the tip of the fin here will be the same as that of the surrounding ambient temperature. So, that point we have to notice. Then, the temperature of the fin at its tip, that means at the end of the fin, at its tip will be same as ambient fluid temperature. Then the temperature at that is, what is the second boundary condition now? It becomes at x is equal to infinity, T will be equal to the T infinity. This is the second boundary condition. Second boundary condition for the first case. This is the second boundary condition for the case 1. Okay, we understand when the fin is infinitely long, the base temperature cannot be sensed at the tip of the fin. So, at the tip of the fin, the temperature of the ambient and the temperature at the tip of the fin will be both are equal. So, we got both the boundary conditions, two boundary conditions we got, we can get two constants. Once we get the two constants here, we got the temperature distribution. After all, what is theta? Theta will be T minus T infinity, right? Theta is T minus T infinity. So, m is root of Hp by Ka, we already know it, its units are per meter. So, once we get C1, C2 from those two boundary conditions, now it means we got the temperature distribution. So, now I am not writing the intermediate mathematical steps, I am giving the solution directly. We do just, it is in the fin analysis, it is just sufficient to remember the boundary conditions for each case, and for each case, what is the temperature distribution, final formula, that is sufficient to remember to do any gate problem. So, for each case of the fin, three cases are there. What are the boundary conditions? Number 1, what is the final solution for the temperature distribution, and what is the resultant heat transfer rate for each case? Then the temperature distribution for infinitely long fin for infinitely long fin is theta by theta naught is equal to T minus T infinity by T naught minus T infinity is equal to e to the power of minus mx. Please remember this formula. This formula must be remembered as the temperature distribution for the infinitely long fin case. This is the first objective, we got it. This is the first objective, we have got it, where m is the root of hp by ka for the infinitely long fin, for very long fin. Okay, first objective we got. Then what is the second objective? What is the rate of heat transfer through the fin? To get the rate of heat transfer through fin, just you for any fin case, how to calculate the, for any fin case, okay, to calculate rate of heat transfer, from entire fin, from the whole fin, from entire fin, to calculate rate of heat transfer from entire fin, just write, we have to write only one thing, that is the Q conducted into fin at its rate, at its root. Q conducted into fin at its root or base. Heat conducted into fin at the root of it. It is the general heat transfer rate from entire fin. How did I mention that? I would like to explain you like this. For example, for that I have taken the pin fin example. Supposing if this is a fin, maybe finite long, infinitely long or finite, but definitely we know that temperature changes in the direction of the x. This is the x direction. This is the T infinity. If you take the entire fin as the control volume, if you just take the entire fin as the control volume, this is the control volume, and this control volume is under steady state. So my argument here is, for steady state of this fin, whatever the heat conducted into the fin at its root should be equal to the heat convected from the entire surface of the fin to the fluid. Then only this control volume will be at steady state. Look at this. If you just take this as the control volume, the total convection heat transfer rate taking place from the entire fin to the fluid should be equal to the heat conducted into the fin at its root, that is at x is equal to 0. Heat conducted into the fin at its root. This should be equal to the total heat convected from the entire surface of the fin to the fluid. That rule is valid for any case of the fin. Please keep this point, very important point, in mind. If you want to calculate the total heat transfer rate from the entire fin to the fluid, just obtain heat conducted into the fin at its root. Okay. When you talk about the conduction, what is that law that comes into picture? Fourier law. Minus Ka dt by dx, Fourier law, where at x is equal to 0, because this conduction, no, we want. So, I repeat once again the statement. For any fin case, I have written this one very clearly. For any fin case, heat conducted into the fin at its root should be equal to the total heat convected from the entire surface of the fin to the fluid. Then only that how did I write this? How did I write this? For steady state. This logic is for, because the fin is under steady state. For steady state, we have already assumed that for steady state, the Q through the fin, to the Q heat loss from the entire fin should be equal to the Q conducted into the fin at its root. So, just to calculate the heat transfer rate through the fin, that is the second objective. Calculate the heat conducted into the fin at its root from this Fourier law. Now we got therefore, for case 1, heat transfer rate through entire fin will be given as square root of, please remember this formula, HPKA into T naught minus T infinity. How did you get this, you may ask? Because we have already given this temperature distribution, right? Temperature, no? You bring this here. What is the dt by dx? You have to differentiate that function and dt by and after differentiation put x is equal to 0. So then you substitute that, just you have to get this dt by dx. To get this one, you bring this T naught minus T infinity here, T write as a function of x, differentiate with respect to x. After differentiation, put x is equal to 0, multiply with minus Ka. Then you will get this particular. Please remember this formula also. This is the heat transfer rate through fin for very long, case 1. What is the case 1? Very long fin, infinitely long fin. Understand that, because T minus T infinity by T naught minus T infinity is equal to e to the power of minus mx. Therefore, T is equal to T naught minus T infinity into e to the power of minus mx plus T infinity. What is dt by dx? T naught minus T infinity into e to the power of minus mx into minus m, because differential of constant is 0, T infinity is a constant. Put x is equal to 0. Implies what is dt by dx at x is equal to 0? T naught minus T infinity e to the power of, when you put x is equal to 0, this will become 1. So it becomes minus m. You substitute that one here. Q conducted at root. Q conducted at root minus Ka dt by dx at x is equal to 0. Right? If you substitute that one here, it becomes minus Ka into T naught minus T infinity into minus m. This minus it becomes plus. This minus, this is plus. Okay. And m is equal to, what is the m value? Root of hp by Ka. We already know that m value is given as root of hp by Ka. If you substitute that, you will get square root of hp Ka into T naught minus T. This is a proof. This is a proof how you got the heat transfer rate through fin like this. So my only one argument you have to remember always is to calculate the heat transfer rate through entire fin. See, after all, fin is there to enhance the heat transfer rate. If somebody asks you what is the total heat loss from entire fin to the fluid, means just obtain heat conducted into the fin at its root from the Fourier law like this. That is this. This is a heat conducted into fin. Heat conducted into fin at root. That is the total heat loss from entire surface of the fin to the fluid. That rule is valid for any case. Need not be case 1. There are 2 other cases, that is fin is finite in length, the tip is insulated, and this is the infinitely long fin. This is theoretically not important. The case what we have done, it is theoretically not important because we never use the very long fin. For that matter, we always design short fins. Please keep in mind that we always try to design the moderately short fins only. Long fins are uneconomical. It's a waste of money, waste of material. So the case 2 is very important. Almost in every fin problem, we will be writing the case 2. What is that case 2? Fin is finite in length, but the tip is insulated. I will give that solution for both heat transfer rate and also the temperature distribution for the case 2, which is a very important case called as a finite in length, but the tip is insulated. When the tip is insulated, when the tip of the fin is insulated, there is no convection heat loss from the tip. Okay, when there is no convection heat loss from the tip, there can't be, when there is no, supposing if this is a fin, there is no convection heat loss from the tip edge because it is insulated. Then what is the heat conducted into the tip? 0. Because convection is 0 from the tip, conduction into the tip also will become 0. Why convection is 0 from the tip? Because it is insulated. So, that case we always write almost in every fin problem. But this case, infinitely long fin case, it is only theoretical knowledge, because no fin is very, very long. It is only theoretical purpose, but practically may not be suitable to design a very long fin. Just but remember this case 1 also.